So, for today, since it's like the last time we meet, I'll just tell you a couple of things about quantum mechanics just to compare like from a mathematical perspective to what we discussed before in Hamiltonian mechanics. And if I have time, I'll tell you a little bit about qubits and that stuff because it's kind of like fun. But see. So first, just as a comparison. So let me put here like classical mechanics, and then I'll put that quantum mechanics. So um, when we were talking about classical mechanics, the main focus of attention was like this thing, the Hamiltonian, right? Like so, the Hamiltonian, which usually I call H. It was a function of position and momentum. Like it can depend on more variables, but now when I'm writing things here, I'm just thinking it's just like a particle in one dimension. So it has like a x coordinate for position and the momentum is p. And in the most standard case, it's like p squared over 2m plus the potential function, right? So the equations of motion for coming from the Hamiltonian was a system of equations, right? Which if you let me put it like this. If you define like a vector x p, then the Hamilton's equations were like you know equation for how these two coordinates change over time, and it gave you something like this. Where here J was this matrix, I think the -1 was on this center. Okay, so that is how the equations looked. And one of the things, like for example, that we had seen is that well, since the equations are first order in time, right, it's a system of equations, so, but they're first order in time. So to solve it, you will need to specify the initial momentum and, the initial position and the initial momentum, right? And so that is conveniently represented in what we had called the phase space. Which are all the possible positions and momentums that the particle could take. And one of the things that I had told you is like, let's suppose that maybe you don't know you don't know exactly what the initial position and initial momentum of the particle is. So maybe the initial position and momentum, you just know that it is somewhere in this region. Then the Hamilton's equations have the property that after any amount of time, so maybe this is like where the position and momentum is located at time 0, right? Well, time t is going to be somewhere else, right? So this is, since there was like an uncertainty, if you want to think about it in those terms of where it was located originally, then at time t is somewhere else. And one of the properties of these equations is that it preserves like the size of these regions, which was so these have, well, because in this case, I'm drawing everything in 2 dimensions. I'm like, these would two regions would have the same area, right? Area is preserved. In more generality, right, when there are like more coordinates for position or for momentum, when there are several particles, you don't talk about area, you talk about what's called measure, right? Or volume, or hyper volume if you prefer. And so that happens because this vector field is what's called divergence free or like incompressible. Okay, so this is like Liouville's theorem. So this is divergence free. Divergence free. So the divergence of this vector field, like we had computed it a long time ago, but that forces like the kind of like the areas of the regions to be preserved. So in classical mechanics, like the evolution of a system is given in such a way that like the sizes of the regions in phase space do not change. Like the shape can change, but not the area or the volume measured. Okay, so what is the okay? So this is kind of like the general setup for classical mechanics, and then what is the idea in quantum mechanics? So there, you still have a Hamiltonian, which is just to distinguish it. Usually, you put like a hat on top of it. So I'm going to state everything pretending that we're working in finite dimensions, so that it's just easier to say without like trying to introduce a lot of baggage in terms of terminology. So I'll do it like what's called like finite dimensional quantum mechanics. So that applies to things like spin, quantum computation, like it does have like many applications, like just like restricting to this. If infinite dimensions, everything more or less works the same, but you just have to be super careful about like, because like it does depend a lot on analysis. But in quantum mechanics, infinite dimensions is basically linear algebra or like specific topic of linear algebra in terms of the mathematics. So here, the Hamiltonian is going to be a matrix. Okay, so it's going to be a matrix. And let's say n by n. Okay. And it is a complex matrix. So in quantum mechanics, you do have to work with complex numbers as kind of forced on you. Okay. But it is self-adjoint. So like we have talked about this before. So it's like a self-adjoint matrix. So the adjoint of a matrix was the conjugate transpose, right? So equals its conjugate transpose. Okay. So if there are no complex numbers involved, it's just saying that it equals its transpose, which is kind of symmetric, right? Right. So when there are complex numbers involved, it is the analog of being symmetric for matrices. Okay. And then the analog of okay, so the thing that it changes a little bit, but formally it's kind of similar in this case is that you still have the Hamiltonian, and then before like the equations are for like take position and momentum, okay? Now the equations like, well, in this context, let's just say like Hamilton's equations is really what you call like the Schrodinger equation. So that is essentially, but it is really the same. So Hamilton's equations in this case, it's called the Schrodinger equation because he's the one who found it. Called Schrodinger equation. Okay, and the idea is that this is no longer like that's kind of like I mean, if you are interested in understanding what's going on physically, this is no longer like an equation for position or momentum. Like it is a bit more tricky than that. So it is an equation for something that's called the wave function. So it's an equation for the wave function. But if you're a mathematician, like that's just like if you don't care about anything, the interpretation is super easy. It's just like a vector in a complex vector space. So this is like just a vector, which I'll call psi. So it's a vector. Let's see, yeah. Just because that's like the usual notation for a wave function. So it's just a vector in a complex vector space, and because we're working in finite dimensions, it's just a vector of c to the n, okay? Which belongs So like we're working on in complex dimension n. Okay. Or if you want, you can think of this as r to the 2n, right? But it's actually better to think about it as c to the n. And so the idea is that this vector, whatever it is allowed to change on over time. So this will be like can change over time. So psi can be a function of time. And Schrodinger's equations just tells you how that changes over time. So like it's basically this, like it's just because this psi dt equals minus a h hat. Phi. Okay, so this is like an equation for how the wave function changes over time, and it's saying is you multiply the wave function by the matrix h hat, and after that well, I mean the negative I is just like a scalar, right? So you can do it whenever you want. Here I is square root of -1, and then whatever you get after doing this multiplication as a matrix times a vector, you multiply by -I. So if you compare that, okay, so it's like first order in time, so it's basically this, right? What is J? J was its matrix. The important thing of this matrix is that it squares to minus the identity, right? So the matrix is something, you know, this is a matrix whose square is minus the identity. So essentially that gets replaced in this context with basically minus I, and negative I also squares to -1, right? So it's essentially, if you do negative I squared, that, I mean, the minus goes and I squared is equals -1. So this is kind of like J, that's how you should think about that. So this is like J, and the only difference here is like before it was like the gradient of the function, but the thing is like quantum mechanics is entirely linear. Like it's always like a linear equation. So like Hamilton's equations are not necessarily linear in classical mechanics, but in quantum mechanics is always linear. So this actually corresponds more like to the case where we had discussed it before, where like this was like a quadratic function, and when this quadratic, the gradient is just like this all can be reinterpreted in terms of a matrix. So this part, it really matches this well when the Hamiltonian is kind of quadratic, so that the equations are linear. So all that I'm trying to say is that it is, in a sense, like a linear version of classical mechanics, right? Like of Hamilton's equations, but with complex numbers. So it matches it matches as best as you could hope that mathematical formalism. The only difference is that here, it is equations for something that is very concrete because it's like the position and the momentum. In this case, the equation is for something again, which is a wave function, which it doesn't have like really like a obvious physical meaning, and that's kind of one of like the complicated things about quantum mechanics if you want to understand it physically. But for a mathematician, it's not a big problem because it's just like a vector in a vector space, and that's fine. But yeah, this is not like the position of this, like an electron. This is not the momentum of an electron. It's just something like it doesn't even it's not even like something that's located in space time. Like if you want to get into those things, like it's not. It's a bit odd. But I'll tell you how it's connected to reality in a moment. But at least in terms of the basic equation, it more or less is indistinguishable from there. And so it's a system, it's a linear equation, right? Okay, so like those are the really two important things here. Like this is always a linear equation. So it's like a linear equation. And it's also first order in time, right? Plus it's always first order in time. So to like, if you were to think about it just like as an ODE class, to solve this, you need to know the initial vector, right? Like the vector at time zero to try to find like a solution. So you need to specify the like what you would call the initial wave function. So to solve it, you would need value of the wave function at time zero. You would need the vector psi of zero. So that's like just like the initial condition. Is that okay so far, so good? No. Okay, so like, my point is that in terms of the equation, they more or less look the same. And then there's also like a version of this Liouville statement in this context. So let's again like just to think about this as matrix problems, like so how would you solve this ODE? Like if you thought about if you saw this in an ODE class, how would you solve this equation in ODEs? Like you know, it's better to just think about it like in terms of like notation. Let's just call all this A, just to make it more closely related to what you have seen before. How you solve that? You exponentiate, right? Like it's just, I mean, it is basically an exponential, the definition of the exponential function. Like if this were like just like with vectors with one answer, this would be the exponential, right? So essentially the solution to this equation, and in finite dimensions, that's completely rigorous. Like in infinite dimensions, you do have to be careful. But the solution to this is just obtained by exponentiating. So it's something like this. So essentially you start with the vector or the wave function at time zero, and you multiply by the exponential of like, well, not the Hamiltonian, but like this e to the minus it Hamiltonian matrix to get like the vector at any other time. Okay. So what is a nice thing about this matrix? Well, it's basically this is like, I don't know if you remember last time when we talked about this. This is because H is a self-adjoint matrix, this will be unitary. Okay, so that's, I don't know if you remember like the discussion we had last time about unitary matrices, but the nice fact or the key fact is that e to the minus it H hat is unitary. Sometimes the matrix is called U sub t for like saying like the matrix at time t is this thing. Okay, so what does that mean? It means that it is, what is a unitary matrix? It is the analog of a rotation matrix, like in complex dimensions. The determinant, I mean, more or less, like because I mean, if the determinant is one, is really like that, but think about it as some sort of complex rotation. Like that's the best way to to regard this as. Okay, so this is even like better than like before in terms of like what's happening here. So let's say that you have some vector space like C to the N, right? So again, like one way to think about this is like maybe you don't know the initial wave function at time zero. So like you know like the initial state of the system is some vector here, but you don't know where it is. Okay. And then at time t, when this evolves, um, well, essentially, like because it's kind of like a rotation, the volume is preserved, right, of the region, but it's even better than that because it's like a rotation. So it's not even, you cannot even translate it or anything. It is really like just rotating it, like I mean, like you can do like a reflection, there are other things involved, but I'm just trying to say, not even translations would be allowed. So then, like more or less, like all of the shape gets preserved. Like it's not like here, like maybe this could have started like a disc and then looks like a triangle, the shape. Here, like qualitatively, it's more or less the same shape. Like it is like a more like um it respects more like the initial data in that sense. Like it distorts less like the initial configuration of the system. So it's more like again, it's almost like just rotating, like so the way this evolves, like it's saying like you have a vector, and that way this evolves over time is just by rotating. Like whereas here, like it could have done all sorts of different crazy things, but in quantum mechanics, like the only thing that happens is like a rotation, basically. Again, the unitary is a bit more than a rotation, but it's more would be like a reflection of things like that. But it is very under control. That's what I'm trying to say. So yeah, so like if I get to the example of the qubit, the idea is that when you talk about quantum computation, like you have like this kind of gates that takes a qubit into a new qubit, but those transformations like have to be unitary because like the point of quantum mechanics is that all transformations are like the way a system evolves can only be unitary. Like and so when you try to represent like certain logical operations on a qubit, you have to represent them by unitary matrices basically. Okay. Um, that's that. Okay, so this is so far like kind of I mean, if you think about it, like this picture is almost like word by word exactly the same, and even gets better in quantum mechanics because like the properties are nicer. It's like linear algebra, rotations, like so in that sense, it's like like mathematically, it's like has like even nicer features than in classical mechanics because you can kind of like use all the tools of linear algebra to describe this. Okay. Okay, so just to like so there are two things. Okay, so like everything now looks like like a rosy picture. Like everything, like your life has improved because like everything is way better. But then like there is a reason why like quantum mechanics is a headache, right? So there are like two like the really kind of like so there are two important features of quantum mechanics that is where like the paradoxical behavior starts. Like so one has to do with entanglement, which I'll tell you what that is, and the other has to do with how the measurement theory is supposed to work. So those are like really like the two things where like all these nice edifice kind of like, I mean, entanglement actually is very cool, but so it's not necessarily like a bad feature, but it is confusing if you have never thought about that. So let me just let's start with entanglement because that is kind of like completely, settled. The measurement thing is kind of where a little bit of controversy there's still around because there are many ways to try to interpret what's going on. But let's start first with entanglement. I don't need any of this. It's just like I think that's how it's written. Okay, so let me start first with classical mechanics just to kind of show you what like happens, which is kind of completely expected, and there's no entanglement here. Like so. Okay, so here is like an example. So to discuss entanglement, you do have to talk about composite systems. That's how they're called. Like so, more than one particle, for example. So in classical mechanics, suppose like now let's think of this as like actual like the plane. So let me put like an X and Y here. Let's So let's say you have like a particle, you have like a single particle, right? I'll put a one to say that's particle one. Okay, so how would you describe that particle? Again, like if you think about it in classical mechanics, you need the position and you need the momentum. Because now you're in two dimensions. Okay, the position is really like x1, y1. In fact, like let me put them like this: x1, y1. And there's like a momentum for each direction, right? Like just like the velocity in each direction, basically. The momentum is just that times the mass, like in the straightforward case. So let's call it P1 and let's see. Bad notation, but I just mean the momentum of the first particle in the x direction, the momentum of the first particle in the y direction. Okay. Okay, but now, what if you had like a second particle around, right? So if you had a second particle, what would you need to describe the second particle? You would need to describe it like x2, you need like the position for the second particle. So that's like two entries, right? Because the particles are moving on the plane. And then you have like, you need the momentum for the corresponding second particle, right? Right. And in principle, the Hamiltonian, the Hamiltonian in this case could be like a function of all of these things, like position and momentum. So like just let me use vector notation, that's why it's convenient. So like it depends on the position of the first particle, the momentum of the first particle, the position of the second particle, right? And the momentum of the second particle, right? So in this case, like if what would be the phase space, like these like equations, like to specify the system, like what you would think about it is that you need to specify the initial position and the initial momentum for each of the particles. So the phase space in this case is 1, 2, 3, 4, 5, 6, 7, 8. You need 8 specifications. So the phase space is kind of like a R to the 8, if that makes sense. So the phase space. Okay. So, but what's a better way to think of this? It is, okay. To think about it better, like it just kind of generalize this idea. Like if you had like, instead of two particles, you have 1, 2, maybe 3, and now n particles, right? Let me put n with capitalized so that it's not confused. So each of these, like, okay. Right, each one, like, because they're on the plane, it has two coordinates for position, two coordinates for momentum. This one has two coordinates for position, two coordinates for momentum. This one has two coordinates for position, two coordinates for momentum. And then this one has two coordinates for position, two coordinates for momentum. Right? So each of these contributes 4 coordinates or 4 like functions, right? So how many things you have to specify here? Like the Hamiltonian will depend on the position of the first particle, the momentum of the first particle, the position of the second particle, the momentum of the second particle, blah 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 blah, up to the nth particle, the position of the nth particle, and the momentum of the nth particle. Okay. Also, the phase space is going to be what? It is R to the, what number should I put, the exponent should I put? What do you think? Well, each one is giving you four things, right? Like the vectors here have size 4, so like there are n particles now, so it's 4 to the n. Okay, and if the particles, like if the particles were in three dimensions, like, like the phase space would be R to the 6n. Okay, so the important thing is that these, like, what is the dimension of the phase space? So let me just write it here. If the particles live in R3, the phase space would be R to the 6n, which is probably more closer to what some of you may have seen. The phase space. Okay. So what's the point of all of this? Regardless of of this, is like that the dimension for this is like proportional to the number of particles linearly. So it's like the phase space grows linearly with the number of particles. So like the dimension of R to the 4n is like 4 times n, and the dimension of R to the 6n is 6 times n. So the phase space grows linearly in classical mechanics, like the dimension of the phase space. So in fact, like more generally, what I'm trying to say is that the way to think about classical mechanics when you have a composite system, you mean just meaning like multiple particles or components, is that the phase space is like a Cartesian product of the individual phase spaces. So in classical mechanics, let me call that Cm, the phase space of the total system is it's a Cartesian product of the phase spaces of the individual systems. Okay. But okay, so that's the situation in classical mechanics, and so the idea is that to know the system there, what does it mean to understand the system in classical mechanics? It means to understand how the positions and the momentums are evolving over time. But now, what's the situation in quantum mechanics? So in quantum mechanics, let me put it like this. So let's say you had like a particle here. Again, in quantum mechanics, the particle is not described by position of momentum, which is like the weird thing. It's just described by this wave function. So instead of assigning to this, even if you thought of the particle being in space and time, you just assign the wave function to it. So that's what characterizes this particle is just a vector in a vector space. So here you have like a wave function in some vector space. So like I'll just write it like this. Okay. And then if you had uh, like a second particle, then you would have a second vector, a second wave function in another vector space. The vector spaces could be the same or not, depending on what the particles are. So actually, they don't have to be necessarily the same, so it's better to leave it like that. Um, and then if you had a third particle, then that would be assigned a third vector in some other vector space. Okay? Um, and in general, what's happening? So in quantum mechanics, what occurs is that to describe the total system, right? Like, so to describe what the thing in the way I'm kind of like putting it in this situation, let me start with this case. If you have it like that, then like the vector that you would assign to the total system, that's just how it works, is the tensor product of these vectors. Like that is just how the the rules of the game work there. So you describe to it, in this case, you would describe to it psi1 tensor psi2 tensor psi3. Okay, so I don't know if you remember like how the tensor product worked last time, but if you have concrete vectors, let me just remind you how it went. Like, let's say that the first vector was like 1, 0, and the second vector was 1, 1. Okay, so what was the tensor product of this? Like, it's 2 times 2, so it has 4 entries. Okay, so you multiply everything together, right? So 1 with this, like 1, 1 gives you 1, 1, 1 gives you 1, 0, 1 gives you 0, and 0, 1 gives you 0. Okay, so that would be the tensor product of those two vectors. Um, and then we can even keep going. Like, what would, like, you could, like, what would have been 1, 0, tensor 1, 1, tensor, what? Let's just do 0, 1. Then, oops. Well, the first two we already found is associative, by the way, the tensor product code, thankfully. So it's 1, 1, 0, 0, tensor 0, 1, right? So 4 times 2 is 8. So now you need something with 8 entries, right? So it's 0, 1, 0, 1, and then 0, 0, 0, 0. Okay, so already here, you can see that there's a difference, right? Because this is growing like multiplicatively, right? Like the vectors have like you know, the entries, like, the output vector that you end up with has a number of entries equal to the product of the individual entries. So this belongs to something like, which has dimension what? Equal to dimension equal to the product of the dimensions, right? Like dimension of V1 times the dimension of V2 times the dimension of V3. Okay? So in general, in quantum mechanics, like, let's just, as to simplicity of notation, let's say that like the vector space for all of them is the same, which, so like if you had n particles in quantum mechanics and all of them have the same vector space associated, same V for all of them. Then the wave function for the system, is a vector psi that belongs to the tensor product of these vector spaces. And this, you're doing this n times. So what the dimension of this? The dimension of this is dimension of v to the n, which is dimension equal to the dimension of v to the n. Okay, so here, like the dimension grows linearly, right? With the number of particles, for example, but here, like the dimension goes exponentially. So that's why, okay, so this is exponential growth. Okay. So like in quantum mechanics, like the composite system has a vector space. This exponentially larger than the vector space of the individual pieces. Okay, which is why, like, if you have seen like all these like stuff about quantum computers and things like that, the great promise of them is that certain algorithms, they should be like, I mean, there's somewhere you have it has been proven that they would be exponentially faster to solve than like the classical analog. Like there's this famous Shor's like factorization algorithm and other things where like a lot of cryptography just depends on not being able to factorize like large numbers efficiently, but there are like algorithms that would use quantum computation to kind of like solve that. I think in polynomial time or something like that. Okay, but it is related. I mean, it's not exclusively related to this fact, but the fact that you have to take the tensor product contributes to why that would be possible here. The entanglement part, where like that is not okay. That's kind of interesting, but it's not like the really odd thing here. So the entanglement part, I don't know if you remember, like we discussed this last time. If you have a vector in a tensor product, it's not always of this form, right? It's not always a product of individual factors. Okay, so the weird thing, like, right, is that once you have a vector in a tensor product, not every psi inside the tensor product, right, is of the form, remember, like those were like called simple vectors. So not every vector in a tensor product is simple. And the interpretation of that is that in the simple case, you really can think that each of them carry its own wave function. But in the general case, like that's what the entanglement part comes in. What happens when there's entanglement is that like the individual subs, like there's not really like a proper notion of like a subsystem because everything is kind of correlated with everything else. So there's no way to kind of like, I say, oh, this is like the wave function for the first particle or the wave function for the second particle. There's just like a single thing describing everything. Like you cannot kind of separate like the total into the, I mean, if you want to sound like, this is why I like people creep in with new age and all that stuff. You cannot really separate the total into like a sum of the parts. Like mathematically, if you want to make that precise, it's just saying, oh, not every vector is like a simple vector in a tensor product. So there is no way to, in this case, there's no way to assign like an individual vector to like the subsystem. So there's just like a single thing, like, which is kind of like odd. So there's no um, individual wave functions for the subsystems. Okay. And that actually can give you like an example, which is with this EPR paradox. But before going there, like, and that kind of shows a little bit nicer how like this entanglement thing works. Before going there, I have to tell you a little bit about measurement, and then once I do that, I can tell you what's happening here. Is that okay? Are there any questions up to now? So far, so good. Okay, so what's left? Let me see. Should I? Okay, yeah. Right, so just to give you like a cute application of how the entanglement works, I do have to tell you something brief about measurement. Okay, so the thing, as I was saying, like the odd thing here is that the wave function is not really something like quite physical in the sense it's not like something about position or momentum or anything like that. So okay, so where is the connection with like the rest of like physics or like the rest of like nature where like they're like you measure position or momentum or angular momentum or energy or things like that. And that's like the measurement part. So like the idea in quantum mechanics is that again, and this is where like it gets a little bit more like tricky how you state it, but I kind of will state it kind of like how you would find in most textbooks. So there's a bit more like controversy here on how you should say things. But the idea is like if you want to measure something in quantum mechanics, the recipe like more or less is to associate like a symmetric matrix to that quantity that you want to measure. So like if there's like a quantity you want to measure, which that could be position, momentum, spin, which I'll tell you about later in a second. Angular momentum, energy. Okay. The point in quantum mechanics is to associate to that a matrix. So you don't work, you cannot measure these things directly. You like associate first like an operator, or that's what it's called. You associate this as associate to this like a self-adjoint matrix. Okay. Self-adjoint again just means that A equals its adjoint. So it is again the analog of a symmetric matrix. So what happens, again, I'm just doing this for linear finite dimensions, but there's like an analog in infinite dimensions. What happens if you know, what happens if you associate to this self-adjoint matrix? Once you have a self-adjoint matrix, you have the spectral theorem that tells you that you can find an orthonormal basis of the vector space in terms of like eigenvectors of the matrix, right? So the spectral theorem says that you have like an orthonormal basis of eigenvectors, like have an orthonormal basis of eigenvectors. It's called then psi one. I mean, I'm just going to do a little bit of the notation. Hopefully, it's not too heavy like that. So here, like I'm thinking about like an n by n matrix. So you have like for this n by n, okay, this is not a unique choice, right? But it's fine. You have an orthonormal basis of eigenvectors. Um, okay. And so I'm just specifying that there are eigenvectors of the matrix A. So like in the sense that A times psi I A would be lambda I times psi IA, where lambda I is the corresponding eigenvalue. They don't have to be distinct, but for now, like just how I'm stating things, it's just a little bit easier to notation-wise to assume that they're distinct. That doesn't really make much of a difference. So lambda i's are the eigenvalues, which are real in the symmetric case or the self-adjoint case. So they're real numbers. Numbers. So the measurement postulate of quantum mechanics is that you can only measure the eigenvalues of this quantity. Okay. So if you wanted to say to measure position, momentum, spin, angular momentum, whatever, the only things when you do a measurement of those things, what you will obtain is one of the eigenvalues. So the eigenvalue postulate. So you can only measure. So whenever you measure your quantity, when measuring your quantity, They're called observables, by the way, but again, like even then terminology drives some people crazy. So when you measure in that quantity, um, you can only measure, only the eigenvalues can appear in the experimental results. So only eigenvalues can be, only the eigenvalues occur as a result of measurements. Okay. And okay, here's the fun part. This is like the if you have any random vector, right? Like maybe the vector that was this, the vector that was describing your system is not necessarily one of the eigenvectors. In general, because they form a basis of the vector space, any other random eigenvector, any other vector is a linear combination, right? Of these eigenvectors, right? Um, And so, oh, by the way, like, yeah, there's no loss in assuming that these are orthonormal. So like, this, once you have like this decomposition, right? Like it's kind of like the Pythagoras theorem, basically, that the norm squared of this vector is, if these are orthonormal, it's just this. Like, I mean, Pythagoras theorem is just the squares, right? But I mean, here you have to use the modulus because these complex numbers, I mean, these are complex numbers, right? So they could be have imaginary and real part. Okay. And so you divide both sides by side squared. Oh, and you have you have a bunch of numbers that add up to one, right? So where do you see a bunch of which are all non-negative, right? You have a bunch of non-negative numbers that add up to one, like that. Well, what you would interpret that is a probabilities. So it's in fact like the point of like the thing is that you interpret this as the probability that the system would be measuring one of these eigenvalues. So this would be the probability that that when you do the measurement, you get the eigenvalue lambda I of obtaining. Okay. Where this is where like the controversial part starts getting in because well, the first thing to like again, not to get into the weeds in this because I'm just telling you a very quick picture of everything. But the idea is not to think you shouldn't think that the vector had one of those eigenvalues to begin with. It's really only after measurement that like kind of like you find one of the eigenvalues. But the idea is not to think somehow that the vector had like this vector had eigenvalue 3 or 4 or whatever. So like for example, if you're trying to measure like energy, right, which is a Hamiltonian actually, it's not that the system had like a specific energy before the measurement. That is not how you should think about those things. It's just there is like it's just like a random linear combination of things. And after the measurement, then yeah, you do find it in one of these like energy eigenstates, but but not because secretly it was always in one of those to begin with. So that is a complicated part. You cannot like you're not allowed to think that the system has properties before the measurement, more or less, unless you're in an eigenstate and eigenvector. Like otherwise, like you get into paradoxes very quickly. Like it's very easy to show that you get into logical contradictions if you just assume that secretly there's an energy that the system has, and then you do the measurement that kind of reveals it. Like so, that is not the way to think about this. But the point is that it like in a sense that is like where the probability theory enters quantum mechanics in the measurement of like these outcomes. So until then, like the theory is completely deterministic. It just evolves with this like exponentiation of the Hamiltonian matrix. In the standard interpretation, once you do a measurement, all of that kind of collapses, and literally it's called the collapse of the wave function. Like that's how like it's called like in textbooks. And so the measurement somehow brings the system into one of the eigenvectors with those probabilities. But that is the part that, that it does require like more discussion, and so I'm going to avoid it. But this is kind of like how physics, if you ever open like a physics textbook, that's what they will tell you, and they just move on. Like they don't think more about that. But right, if you care about those things and you think about more of those things, and then you see that there are kind of weird things happening there. But yeah, like, well, just to kind of start wrapping this up, yeah, like that's how you get to like the two like famous like well, let's actually let's just do like the spin thing, because I like to have like enough time. So here's like spin. Okay, so what is a bit in in computation or something, or like just basic logic? I mean, a proposition, if you took all math 300 already, right? So a proposition is something that can be either true or false, right? So it only has two possible values, outcomes, right? It's like a binary choice, right? It's 0 or 1, typically how you think about it. Uh, like in quantum mechanics, the closest analog of that is what is called the qubit, which is something because now everything is linear algebra. You are working with vector spaces, so it is a linear combination of two vectors, one that represents like a truth value of 0, and the other or false, and the other true value of true. So for example, like what happens in the case of spin, like here's like like this is like the Theringer like experiment. Like, you have like some particles that you like kind of like a beam that produces them, and you apply like a magnetic field to them. Like let's say that it's like a magnetic field like in the z direction. Like let's say that this like vertical direction is z. So what happens is like again like the particles have something called spin, and the result when they interact with the magnetic field is that this ray kind of deflects into two pieces. So some will be deflected up and the others will be deflected down. And literally that's what you would see if you put them, you throw like the particles and you put like a detector, and that's how it looks. So some kind of go here up and the others go down. Okay, so it is a binary choice of the outcomes up or down, which you can think of this as true or false, right? Like in practice, like how do you model like an out like a bit? Like you need something that can be in two steps, right? So um, that gives you the true or false. So it's just two outcomes. Okay. Now, just to make this a bit more precise, like so you're trying to measure like an observable, you're trying to measure something that's called spin, okay? So there is a matrix associated to this that carries like this information. So if you have something like this, like let's call the spin C matrix, because like the magnetic field is in the Z direction. Let's call it SZ. And this one will be like the easiest thing that you could think of. So I'll just put it like as 1, 0, 0, -1. Okay. Okay, this one is very easy. Like it's clearly all the entries are real. So it's that, and it's even diagonal. So it's even easier to check that it's symmetric, self-adjoint, right? And the eigenvalues, this is a diagonal, like it's like are just ±1, right? So it is as easy as you could think. And let's think of the plus eigenvalue. Maybe if you want, you can think about it as being true, and then -1 eigenvalue as being false. Or I'll call them up and down because it's less confusing. So up will be like, if you landed up, it means that you measure like eigenvalue 1. And if you landed down, like that means that you measure eigenvalue -1. So the eigenvectors, I don't know if you have seen like this Dirac notation for vectors, so it's very cute, but like usually the vectors, like if you just like what is an eigenvector for the first eigenvalue is just 1, 0, right? So this right. And so like because this one is the first like the one is in the first entry, I'll call it the up vector. Usually if like again like this is like common in quantum computation, like in physics textbooks, they kind of like do use this Dirac notation for vectors, where like the vector is kind of surrounded by some brackets. So I mean by what's called like a cap. So it's like a vertical arrow together with this like bracket, pointy bracket. But okay, if you don't like it, just think about it as just being 1, 0. Okay. And an eigenvector for lambda equals -1 would be 0, 1, right? That is actually one that works. So yes. And then like 0, 1, and since the one is down, I'll call this the down, up and down, right? Okay. And so if you have if you have like if you know one of these atoms had been this like you can actually kind of do the experiment so that you shoot like like the atoms like one at a time or whatever. So but the idea is like these are a basis for C2, right? So this for like these two vectors form a basis. Okay, so any other vector psi is a linear combination of these two. I'll keep using the notation just maybe hopefully to try to get you used to it. It's a linear combination. So usually these coefficients are just called alpha plus beta. Okay. And then it's like a normal convention to assume that these ones have length 1, and it's also a standard convention to assume that the vector always has length 1. So you can just assume where like that this it happens to be 1. And so like again, like this is kind of like the probability, like the idea is like the way you think about this is that if you do the experiment where all these atoms like are kind of prepared, or like molecules or well electrons, whatever, are prepared in the vector psi, then with probability alpha squared, you measure like you get the result up, and with probability beta squared, you'll get the result down. Okay, so it's only if you can, I mean, you can prepare them in an eigenstate. So like for example, if you just keep the up ones and then you throw this through another Stern Gerlach, they would always come up. So like only when you are in an eigenvector of the matrix, you would always get like a result of 100% for either of them. Okay. And so just to kind of just to start, because I have a little time. So one is kind of like a cute application of entanglement. So for example, that's a qubit in general. Like a qubit is just like a linear combination of an up and down state, essentially. So this is like a qubit. So like again, you can interpret this as true or false or whatever. So like, and so that's kind of like that's the idea, because like when you do like a computation, like you can only get like like everything, if you work in binary, like, like you can only read zeros or ones, like, so it's just like the outcomes can only be zeros or ones, but like the difference is in quantum mechanics, you can be in a superposition of those before the measurement takes place. Okay, so what is like, just to finish this up? So what's like an application of all these ideas with entanglement and measurement? So this is like the EPR experiment. So the idea is that you can prepare like, you can take two of these atoms and you can prepare them, or like molecule electrons, like you can call them however you want for now. And so you can prepare them. Let's put this like. So you can prepare them in a way that they are called like perfectly anti-correlated. So like, like say, meaning that if this one had like spin up, the other one has spin down, or if this one has spin down, the other one has spin up. Okay, so this is like called like a perfect anti-correlation, right? Because one, like the idea is that they kind of cancel out to zeros, like up plus down is kind of zero in a sense. Okay. In terms of eigenvalues, because like the eigenvalues are 1 and -1. So that is like a possibility, right? But then because of quantum mechanics, because the equations are linear, you are allowed to take linear combinations of this, and that's still supposed to represent a possible state of the system. So you can take a vector, which is called like an EPR vector, which is something like this. The 1/√2 is just to make that of length 1. It doesn't matter. You can ignore that if you don't care. Like this is just allowed. Like the laws of quantum mechanics allows you to do this. Oh, I should have put like a tensor product. Maybe that's why it's kind of getting confused here. I mean that like when I just multiply them, I mean like a tensor product. So just to put this a bit more clear. Okay, so it's a linear combination of like these pure states. Okay, and the way you're supposed to think about this is that this one is neither, like none of the two particles are either up nor down. Like it is a combination, like it's just a superposition. There's a real good way to think about what it means. Like there is neither of them is up or down. Like that is the best you can say. Like in fact, you can show that this is not a simple vector. So it is not really a tensor product of two individual vectors. Okay, but then what you can do, let's call one of these particles orange and the other one green. So this is kind of like the one that corresponds to the orange piece. Maybe colors help a little bit. But what you can do is like, for example, you send like in some quantum computing, like Alice and Bob are the go-to names for like experimenters. So you can send like one particle to Alice and the other particle to Bob. Okay, and Alice is then allowed to measure the spin of this particle using like a Stern-Gerlach experiment. So Alice has to measure like the spin of this particle, and the spin of this particle can only be up or down. That's what the quantum mechanics rule says. But imagine, let's just do the experiment, like, let's say that Alice measures like the state in spin up. Well, if she measures the state in spin up, essentially like the idea is that after the measurement, the system has collapsed to this particular subvector, if you want to call it like that. So with certainty, once you measure this one here, once Alice does the measurement of the vector and gets spin up, you know for a fact that Bob will get spin down. There is no way that has to happen for 100% certainty. And in fact, but the idea is that before Alice did the measurement, it's not that the Bob's particle was in spin down. That is not how you're supposed to allow that's not how you're supposed to think of the question. There was no spin up nor down for neither of these particles before the measurement took place. So the paradoxical thing is that, and this has kind of been done in similar experiments, is that you can separate these as much as you like, even more like, you can separate them enough so that light wouldn't be able to travel in like from here to here to be the how should I say that when you do the measurement here, it's kind of like light years away, but somehow the change in the state has been instantaneous. So it's not that the measurement here could have, if you thought that somehow the measurement travels like as like a perturbation in space to affect the other one, that cannot happen because I would need to travel faster than the speed of light. And like if you know special relativity, nothing can travel faster to the speed of light. So the weird thing is that like these two are perfectly correlated. But somehow like before the measurement, neither had spin up or down, but somehow the measurement instantaneously influences the other one, no matter how far away they are separated in the universe. Okay, so I mean, this is like a complicated topic that does deserve like more time to discuss properly, but it does give you like an idea of like the flavor of like the paradox. Like, that is where like quantum mechanics has a lot of like is like more like mystical flavor for those like, who don't do like they like, read it more like in imprecise terms because it does essentially say that there are like all these correlations that remain no matter how much you separated the parts. Okay, but let's finish here. So well, yeah, like in an ideal world, I would have wanted to spend more time on the quantum stuff, but hopefully, like at least some of the mathematical features is plausible how it's related to Hamiltonian mechanics, right? So, but yeah, there are like more to say, but hopefully, yeah, if someone is interested, feel free to talk to me and I can recommend you some other things. But let's just end here. Let me finish. So, yeah, so I'll see you.